Right, let's do some physics. It's paper 2, higher tier, triple award. Figure 1 shows part of a roller coaster ride seen from the side. The roller coaster car rolls down towards point P. The car has a mass m kilograms and a velocity v meters per second. Which of these is the correct equation for calculating the kinetic energy of the car? Well, the kinetic energy is always a half mv squared, so the answer is C. The mass of the car is 580 kilograms. The car gains 39,000 joules of gravitational potential energy as it climbs from P to Q. State the equation relating change in gravitational potential energy, mass, gravitational field strength, and the change in vertical height. Well, the change in the gravitational potential energy equals mass times by gravitational field strength times by change in vertical height. The equation's always the same. Calculate the height h shown in figure 1. Gravitational field strength is 10. So you take the GPE equals mgh equation, rearrange it so that h is the change in the energy divided by the mass times by the gravity. Pop in the change of energy and divide that by your mass times by the gravity, and your answer comes out as 6.7. C. The car enters a pool of water at R, it slows down and stops at S. Describe how the total energy of the system is conserved as the car travels between R and S. So you've got gravitational potential at the top, comes all the way down, turns into kinetic energy, comes all the way back up again. Now what they specifically want is what happens to the energy between R and S. So at R, it's going to have a lot of kinetic energy. It's going to hit the water, and the kinetic energy is going to turn into heat energy in the water, kinetic energy in the water, and gravitational potential energy of water because it's going to fly up. And all of that is because work is done on the car by friction. And if we have a look at the answer, work is done against friction. Energy is stored in some kind of other specific way. So acceptable, the kinetic energy of the water, thermal energy of water, so the water heats up, and thermal energy of air as well. A little bit of gravitational potential energy of the water as it sprays into the air. Question 2. Figure 2 shows a tank for holding water. The tank has sides 2.4 metres, 2.1 metres and 1.5 metres. The pressure at the bottom of the tank is 12 kilopascals, so that's 12,000 pascals. State the equation relating pressure, force and area. So pressure equals force divided by area. Question 2. Calculate the weight of the water in the tank. So if the pressure equals force divided by area, rearrange that so that the force equals pressure times by area. Weight is a force, so it's the force that we'll want to work out. Now, let's work out the area. So the area of the bottom is 2.4 times by 1.5. So 2.4 times by 1.5 gives us 3.6, and that'll be meters squared. Now we've got the area, we can pop it in the equation. So the pressure was 12,000 pascals, and we need to multiply that by 3.6, which was the area. And your answer should be 43,200 newtons. Question 3. Which diagram shows the direction of the forces from the water on the inside of the tank? Well, if it was a balloon and we poked the balloon with a pin, then water would spray out in all directions, so the pressure is in all directions, forcing outwards. So that's B. Question B. Figure 3 shows 3 containers, A, B and C. Each container contains a liquid as shown. So water in that, mineral oil in that, and water in that. Figure 4 shows some data about the liquids in the container. So container A tells you the area, tells you what liquid it is, the density and the depth. B gives you all the areas, etc. And C gives you the same information again. Now the actual question says, explain which container has the highest pressure at the bottom and which container has the lowest. The equation you need is pressure due to a column of a liquid equals height times by density times by gravity. So there's the density, there's the height, which is the depth. So the area is what we call an ambiguous distractor. You don't actually need the area. The pressure due to a column of a liquid does not depend on the area. So your answer for 3 marks should be talking about the densities and the depths. Now if we compare A, the pressure in A is going to be the highest because the density is the greatest and the depth of water is the greatest. B, the depth is quite big but the density is smaller, so that's going to be medium pressure. And C, the pressure is going to be the lowest because even though it's got a high density, it's got a very small depth of liquid. So if I look at the mark scheme, the pressure in A is the highest and the pressure in C is the lowest, so the pressure in B is medium. Yeah, that's what I've just said. Now, the pressure depends on depth of the liquid. So if we compare A and C, we'll see that the depth is half that in C compared to A. So the pressure of C will be half the pressure of A. Pressure depends on the density of the liquid, so if we compare A and B, they're the same depth, but the pressure in A is greater than B. So these two are the same depth, but the pressure in A is greater than B, and that is because the density of A is greater than the density of B. Question 3. The student investigates how the resistance of a thermistor varies with temperature. The student sets up the circuit shown in figure 5 to measure current and voltage. He finds that it does not work. Give 3 modifications the student should make to the circuit so that the circuit works correctly. Well, the ammeter needs to be in series. That's 1. The voltmeter needs to be in parallel. That's 2 changes. And one of these cells needs to be turned around. If we have a look at the answer down here, that's exactly what I've just said. Part B. The student uses the equipment shown in figure 6 to measure the temperature of the thermistor. So a thermometer popped into some water. Yeah, water bath, heater on the bottom of the water bath, thermistor's in there, wires to the circuit and a little bit of a stirrer. Give 1 reason for using the water bath. It's so that the thermistor and the water are at the same temperature. A large volume of water, and that'll end up giving us a steady temperature rise. Part 2. The equipment shown in figure 6 is for investigations in the temperature ranging from 20 degrees to 100 degrees. State 1 way the student could develop this experimental procedure to investigate temperatures outside of this range. If you add some ice that will make the temperature go lower than 20 degrees. And we could replace the water with a liquid that's got a higher boiling point to allow us to go higher than 100. Question C. The student takes measurements for two other components, A and B. The results for these components are shown in figure 7. Okay, so component A, resistance up the side, temperature along the bottom. You can see that the resistance is getting lower as the temperature is getting higher. Whereas for component B, as the temperature is increasing, eventually the resistance increases. And the question says, compare and contrast how the resistances of component A and component B vary with temperature. So, similarities and differences. So the similarities are that the resistances of both change with the temperature. Both graphs show a non-linear relationship, so they're both curves. The data comparison, okay, let's have a little look. So what they're saying is that the resistance of component A at 80 degrees is the same, so 5,000, as the resistance of component B at 80 degrees, 5,000. Differences, well, the resistance of A decreases with temperature, so the resistance is going down as the temperature increases, whereas for component B, the resistance increases as the temperature increases. For A, the largest slope or the biggest rate of change is at lower temperatures, so the resistance is decreasing very fast between 0 and 60, whereas for B the resistance is constant between 0 and 50 degrees. Component A is connected to a 12-volt supply. Which of these is the current in component A when the temperature is 80 degrees C? So component A, 80 degrees C, the resistance is 5,000. So voltage equals current times by resistance. Therefore, current equals voltage divided by resistance. So that is 12 divided by 5,000. So the answer is B. Question 4. Figure 8 shows an airport worker refueling an aircraft. Pumping fuel into an aircraft can be dangerous. The worker connects an earth wire to the aircraft before pumping fuel. Give one reason why earthing reduces the risk of a fire. The earth wire discharges the aircraft to prevent sparking, which could ignite the fuel and cause a fire. So you only get a spark if voltage builds up, and voltage can only build up if electrons builds up. So if you've got an earth wire, it allows the electrons to flow down to the earth so they don't build up. Part 2. Explain how an aircraft can become electrically charged as it flies through the air. So friction between the aircraft and the air causes electrons to be transferred between the aircraft and the air. B. Fuel weighing 230,000 newtons is pumped into the aircraft. This fuel moves upwards through a vertical height of 4.7 meters. The power developed by the pump is 1,600 watts. Calculate the time needed to refuel the aircraft. So energy, gravitational potential energy, equals weight times by height. So that's normally mass times by gravity times by height. Now that is also going to equal the energy transferred is power times by time. So if we rearrange those equations, we can get time, so that the weight times by the height divided by the power will give us the time. So you just pop your numbers in and the answer should come out as 680 seconds. Question C. Figure 9 shows an electrostatic method for spray painting a car door. The car door has a negative charge. The droplets of paint receive a positive charge as they leave the spray gun. Explain how charging the door helps the paint to form an even coating on both sides of the door. You should use ideas of forces and fields in your answer. It's worth 2 marks. So, negatively charged door will attract positively charged paint droplets. Opposites attract. So therefore, the paint will follow the lines of force and will coat both sides of the car door. You could talk about the electric field being directed towards the car, so the positive paint will move toward the door, or as the electric field touches all parts of the door, hence the positive paint will coat all parts of the door. Question 5. A student uses a digital caliper to measure the length of a spring as shown in figure 10. The spring is bendy and difficult to measure. The student takes the 6 readings shown in figure 11. So these are all millimeters. They're all pretty close, but they all differ slightly, and most of them do. Calculate the average length of the spring. So we know, right, this here is different by a lot. So leave that one out in the calculation of your average. So if you add these 5 together and divide it by 5, that should come out as 20.31. Part B. The student investigates the stretching of a spring with the equipment shown in figure 12. So you got a spring here and some weights. It's a standard Hooke's law experiment. The student investigates the extension of the spring using 6 different weights. The results are shown in figure 13. So you've got the weights are increasing by 0.2 each time, and the extension is going up by 4 millimeters each time. Draw a graph of the readings using the grid shown. So they are looking for the axes with a linear scale that uses more than half of each edge of the grid, and you need to label them with the units from the table. So weight would go along the bottom and extension up the side. Weights in newtons, extensions in millimeters. And all points need to be correctly plotted to plus or minus half a square, and a single straight line passing through all the points on the origin. Obviously, if the weight is 0, then the extension is going to be 0. The student writes this conclusion: the extension of the spring is directly proportional to the weight stretching the spring. Comment on the student's conclusion. Well, it's correct, because for each equal increment of force, it's causing an equal increment of extension. In other words, every time that the weight goes up by 0.2, the extension's going up by 4 millimeters. The graph is a straight line and it goes through the origin, which means it's directly proportional. So the student's conclusion is correct. Question C. The student extends the investigation by finding information about the stretching of wires. The student finds the graph shown in figure 14 for the stretching of a wire. Describe the non-linear stretching of the wire shown in figure 14. So we've got the load going up the side and the extension in millimeters going along the bottom. So they're looking for above 37.5 newtons or 4 millimeters. There is a large increase of extension for small increases in load. So in other words, the extension starts to extend a lot, even though the force is only going up by a little bit. The maximum extension of the wire is about 16.5 millimeters before it breaks. So there's the extension there, just over 16, and then it breaks there. And above 12 millimeters, the wire keeps on extending when the load is reduced below 46 newtons. So at 12, that's when we've got our maximum load that it can take. And then after that, we can actually take some load off and the wire will still continue to be stretched. Question 6. Wooden trucks on a toy railway have permanent magnets that hold the train together. The magnets are arranged so that an N pole touches an S pole, so North Pole touches a South Pole between each truck. So North Pole, South Pole, North Pole, South Pole, North Pole, South Pole. Truck Y is removed from the train, turned through 180 degrees, and is then replaced between truck X and Z. How does this affect the train? D. Y now repels both X and Y. So this South Pole here will be reversed over to here. So that'll be a South Pole and a South Pole, so they will repel. And this North Pole will now be over here next to that North Pole, so that will repel. So yes, D is correct. Part B. The structure of a truck seen from above is shown in figure 16. The permanent magnets cause a magnetic field both inside and outside the truck. Which of these correctly shows the field inside the truck? And the answer is C. Remember, field lines travel from the North Pole into the South Pole. So from the north into the south, and they are shaped in a circle like that around the edges, and they are uniform in the middle. Question C. A student investigates the forces between the trucks in the toy railway. She places another truck W next to truck X. She pulls truck Z in the direction shown by the arrow. The whole train travels at a constant speed as shown in figure 17. The student repeats this method of adding trucks and pulling the train each time. When there are 7 trucks in total, the train comes apart between Y and Z, when tested as shown in figure 18. Explain why the train acts in this way by considering the forces involved. And the answer is frictional forces increases as you are adding more trucks. So in order to keep a constant speed, the student must increase the force that she is applying to Z, because if there's more of a backward force, then you need more of a forward force. Now, as she applies the bigger forward force, Y and Z are going to separate, and that's because the frictional forces pulling to the left are more than the magnetic attraction can cope with. Part 2. Devise an experiment to investigate the horizontal force needed to separate the trucks from the engine. 3 marks. Well, you'd need a Newton meter and use it horizontally. That'll work out the force. Record the largest force as you're pulling it and repeat that several times under the same conditions. Part 3. Explain why a larger force is needed to separate the trucks from the engine if the force is applied at an angle to the horizontal. That's worth 2 marks. The applied force must be resolved horizontally to determine the force that separates the engine from the trucks. And since the size of the resolved force is always less than the size of the actual force, then a larger force applied at an angle is needed to separate the trucks from the engine. Sounds like pure waffle. Basically, if you find out that horizontal force was 20 newtons before the trucks would separate, if we use the tip-to-tail addition of vectors, if you're pulling it at a certain angle, then this force here is actually made up of this force and this force. So this force has to be greater than 20. Seven. A straight piece of wire is 0.713 meters long. It is placed at right angles to a uniform magnetic field of 0.47 Tesla. The force on the wire is 0.089 newtons. Calculate the current in the wire. Use the equation sheet from the formula. Use the equation from the formula sheet. Give your answer to an appropriate number of significant figures. So the equation that you need to use is F equals Bill. Magnetic field strength times by the current times by the length. So they are rearranging that. So there's your force, there's your magnetic field, there's the length. Your answer should come out as 0.27 to 2 significant figures. Part B. The student investigates the relationship between the magnetic flux density and the electromagnetic force on a current carrying wire. The student has the equipment shown in figure 19. The student varies the number of magnets and measures the force on the wire using the force meter. So that's the number of pairs of magnets, 1, 2, 3, and the force on the force meter is 0, 0, and 0.1. The student decides that his equipment is not sufficiently sensitive. Give 3 ways the student should develop his investigation to improve the quality of his results. That's for 3 marks. Right, he needs to use a higher current as the force depends on the current. So that's this force here on the wire depends on the current. Use more or stronger or a larger range of magnets. Use a force meter with a smaller range. So that's going from 0 to 10. We could probably just do with 0 to 1. Use a longer distance from the pivot to increase the moment of the force on the wire. So basically, as this side of the wire is going up, this side of the plastic is going to go down, and that's going to pull this Newton meter downwards. So that's how that experiment works. C. Figures 21 and 22 show different voltages that can be applied across a wire. Explain which of the voltages in figure 21 and 22 cause an alternating current in the wire. If the voltage changes sign, so it goes from positive to negative, then the current is changing direction. So in figure 21, the current is AC because the voltage is changing sign. And in figure 22, the current is DC as the voltage is always positive. That's positive and then negative, so that's AC, positive, negative. Whereas this, a load is going up and down, the voltage is always positive. D. A power transmission wire hangs so that it is at right angles to the Earth's magnetic field. Although this magnetic field is constant, the cable experiences a changing force. Explain why the force experienced by the cable changes. The transmission wire carries an alternating current. The force is caused by this current, which varies in size and direction. The direction of this force depends on the direction of the current, so the direction of the force also changes. And the magnitude of this force depends on the magnitude of the current, so the magnitude of this force also changes. Eight. Figure 23 shows an electric car connected to a battery charger. The car has a rechargeable battery to drive its motor. The rechargeable battery provides a potential difference of 330 volts and can store up to 64 megajoules. It takes 8 hours for the battery to receive a full charge, assuming that the charging process is 100% efficient. Calculate the total charge that flows when the battery is being charged. So the equation we use is charge equals the energy divided by the voltage. Substitution including change of unit. So we've got 64 megajoules equals 64 million joules, remember. Pop that into the equation. That's your energy, that's your voltage. The answer comes out as 190,000 coulombs if we've rounded it up. So it should be 193,939. B. Calculate the average charging current. So the current is the charge divided by the time. Remember, 190 kilocoulombs is 190,000 coulombs. Convert your time, 8 hours, into seconds. So remember, there are 60 seconds in a minute and there's 60 minutes in an hour. So there's 3,600 seconds in an hour. And there's 8 hours, so that comes out as 28,800 seconds in total. So that's 190,000 divided by 28,800, and your answer comes out as 6.6. That's it actually over there. Part C. The battery charger shown in figure 23 is connected to the 230 AC volts domestic mains supply. The output voltage of the charger is 335 volts and it provides a DC charging current. Charging stops if the charging current exceeds 15 amps. Explain how electrical components in the charger can be connected together to give this type of output. So for 6 marks, what they're looking for is that you say how you're going to change the voltage, how you're going to convert the direct current. Convert AC to direct current, DC, followed by how you're going to limit the current. So if you say that a transformer is going to be needed to step up the voltage, that's how you'll change the voltage. A diode would be needed to change AC to DC. Remember, a diode only allows current to go in one direction. So AC, it's only the positive part of the current that will come through. And the charging current can be limited to 15 amps by using a fuse or a circuit breaker. You might want to say that a circuit breaker would be better than a fuse, because a fuse would need to be replaced once it blows. The transformer primary coil would need to be connected between the live and the neutral in the primary circuit. The live wire brings the current into the transformer and the neutral would take it away. The diode would be connected in the secondary part of the circuit, and all of those components, so the battery, the diode, the fuse, the secondary coil, they should all be connected in series in the secondary part of the circuit. Quite a tricky one. Question 9. Figure 24 shows a submarine underwater. The motor in the submarine turns the gear wheels shown in figure 25. So gear A is turning clockwise and has 30 teeth, and gear B would be going anti-clockwise. It's got 20 teeth. Gear wheel A rotates clockwise through one complete turn. Which of these is correct for gear wheel B? The answer is B. We know that it would be going anti-clockwise, so we can rule out A and C straight away. And the ratio of 30 teeth to 20 teeth is the same as 60 to 40, which is 3 to 2. So every time this turns twice, this one will turn 3 times. So for one full rotation of this gear will rotate 1.5 times. Because 1.5 times by 20 would equal 30. When you've got the teeth, it's still a 1-to-1. For every one tooth that this has got, it'll make one tooth of this turn. B. A bubble of gas escapes from the submarine. The volume of the bubble is 23 centimeters cubed. The pressure of the gas inside the bubble is 297 kilopascals. The bubble rises to the surface without change in temperature. Calculate the volume of the bubble when it reaches the surface. Atmospheric pressure is 101 kilopascals. Use an equation from the formula sheet. It's worth 3 marks. So the formula that you need from the formula sheet is pressure 1 times by volume 1 equals pressure 2 times by volume 2. You need to rearrange that to get volume 2, so that'll be pressure 1 times by volume 1 divided by pressure 2. Pop the numbers in, make sure that you remember to convert kilopascals into pascals by multiplying it by 1,000, in other words putting it times 10 to the 3 on the end. And your answer should come out as 67.6 centimeters cubed. That's the full answer. Question C. A student is interested in the way that submarines are controlled. She has several regular wooden blocks, a set of weights, and a tank of water. Wood floats in water. The student plans to immerse the wooden blocks fully in the water and investigate the relationship between the upthrust and the weight of the water displaced. Describe how she should determine one of the variables in this investigation. So it's probably easier to calculate the upthrust. So you'd find out how many weights you needed to add to the back of the block until the wood is fully immersed, and then record how much load that was on the back of the wooden block. And then you'd have to calculate the upthrust by adding the load you've just worked out required to make the block fully submerse, and add that to the weight of the block itself. And the upthrust will be the load plus the weight. The other way of doing it, if you wanted to investigate the weight of water that's displaced, use a ruler to measure the dimensions of the block and multiply them together to find the volume of the block. And the volume of the wooden block will be the volume of the water that gets displaced. So calculate the weight of the water using volume times by density times by gravity. If you don't know where that comes from, so the weight of the liquid displaced is mass times by gravity. Now remember, mass is density times by volume, then obviously multiply it by the gravity. So that's density times by volume times by gravity. Question D. Figure 26 shows a submarine stationary and submerged at a depth of 10 meters. Explain how pumping water into and out of the buoyancy tank affects the depth of the submarine below the surface. So upthrust is the force on the submarine in the water when it's submerged in a fluid. Now the upthrust on the submarine and its weight act in opposite directions. So your weight's going down, upthrust's going upwards. Upthrust is equal to the weight of water displaced by the submarine. The difference in pressures on the upper and lower surfaces of the submarine causes the upthrust. The upper part of the submarine here is not as deep as the bottom part. So you get less pressure on this part of the submarine because of the column of water above it compared to here. The column of water above the bottom part is bigger. So you get a bigger pressure here. So the upthrust is the difference between the pressure acting on the top compared to the bottom. The volume of the submarine is fixed, so the upthrust on the submarine is constant. However, if you increase or decrease the volume of water in the tanks, that's going to increase or decrease the weight of the submarine. Now that will not affect the upthrust, but if the weight increases to become greater than the upthrust, there is a resultant downward force on the submarine, so the submarine will sink. If the weight decreases to become less than the upthrust, there is a resultant upward force on the submarine, so the submarine rises. Once again, pretty tricky stuff. Question 10. The espresso machine shown in figure 27 is an electrical appliance. The espresso machine has an electrical heater connected to a 440 volts main supply. The power of the electrical heater is 3.5 kilowatts. The rating of a fuse is the current above which the fuse melts. Which of these is the most suitable fuse for the espresso machine circuit? And the answer's C. How do you work that out? Well, what have we got here? We've got a power, we've got a voltage, we're looking for the current. Is there an equation that connects these? Yes, there is. Power equals voltage times by current. So therefore, current equals the power over the voltage. The power has to be in watts, not kilowatts. Divide that by your voltage. That comes out as 7.95 amps. You always choose a fuse that is slightly bigger than the normal operating current. Otherwise, the fuse would constantly blow during normal operation. So we would choose fuse C. Although fuse D is bigger, it's too big compared to current. So just go for the 10. Question 2. Before the espresso machine can be used, its heater must raise the temperature of some cold water. The specific heat capacity of water is 4,200 joules per kilogram Kelvin. Show that it takes the heater about 90 seconds to raise the temperature of 1 kilogram of water from 18 degrees C to 95 degrees C. Use an equation from the formula sheet. So the equation you want to use is the change in the heat energy equals mass times by specific heat capacity times by the temperature change. Now the energy will also be equal to power times by time. So if we combine this equation with this equation, then we can rearrange that equation in order to get the time. So it's mass times by specific heat capacity times by the temperature change divided by the power. So 1 kilogram of mass multiplied by the specific heat capacity multiplied by the temperature change. We've gone from 18 up to 95, so that's 77. Now this is saying in kelvins, but remember 1 degree C increase is the same as 1 Kelvin increase. So an increase in 77 degrees C will also be an increase of 77 kelvins. Divide that by the power, which was 3.5 kilowatts, which is 3,500 watts, and that comes out as 92.4. Part B. The espresso machine has a steam pipe that can be used to heat milk in a jug, as shown in figure 28. Steam from the pipe enters the milk where steam condenses to water. The steam and hot water heat the milk. Describe in terms of energy how the arrangement and movement of particles in the steam changes as the steam enters the milk, condenses and cools. So when steam condenses, its molecules move closer together, so the internal energy is going to decrease. And when the water from the condensed steam cools, its molecules move more slowly, therefore storing less kinetic energy. Part 2 tells you the specific heat capacity of milk, the specific heat capacity of water, the specific latent heat of condensation of steam, the temperature of the steam, the mass of the steam that condenses, the temperature of the milk. It's telling you that it rises from 5 to 65. By considering the transfer of energy from the steam to the milk, calculate the mass of milk that is heated by the steam and hot water. Use equations from the formula sheet. So, what you've got here is the steam, the energy from the steam lost is going to be equal to the energy that the milk gains. So we've got the temperature of the steam is 100 and it's going to go down to 65 because the temperature of the steam at the end will be the same as the milk at the end. We need to change the steam into water. The equation we use to work out how much energy is required to change a state is the mass, in this case of the water, multiplied by the specific latent heat, L, of the water. So that'll tell us how much energy is required to change the state from steam to water. Now we need to add that to the amount of energy required to get the temperature of water to change. So you can see that's the mass of the water times by the specific heat capacity of the water times by the temperature change of the water. And that's going to equal, now the milk doesn't change state, so we just need to know the mass of the milk, the specific heat capacity of the milk, and the temperature change of the milk. So that's where this comes from. Now, if you rearrange that, you can find the mass of the milk. Now, we are converting the mass of the milk from 25 grams into kilograms by dividing by 1,000. And that's the specific latent heat. We're converting the mass of the water from 25 grams into kilograms by dividing it by 1,000. Mass of the water. And we need to multiply that by the specific latent heat of condensation of steam. And we need to add that once again to the mass of the water, but in kilograms, times by the specific heat capacity of the water, times by the temperature change of the water. Remember, the 35 degrees is because it's going from 100 degrees C down to 65 degrees C. And we'll divide that by the specific heat capacity of the milk multiplied by the temperature change of the milk. That's the specific heat capacity of the milk, and 60 is the temperature change of the milk as it goes from 5 to 65. And that comes out as 0.26 kilograms. Once again, a pretty tricky question. Give 2 reasons why the actual mass of steam needed to heat the milk from 5 degrees to 65 degrees is greater than 25 grams. And that's because more steam must condense and transfer the energy that is dissipated to the jug during the process. More steam must condense and transfer the energy that is dissipated to the surroundings during the process. More steam must condense and transfer the energy needed to cause the milk to froth. I think the easiest mark to understand would be more steam must condense to replace any steam that might leave the milk without actually condensing. And that's how to take care of that. Thank you very much. I hope it's helpful for your exams, and good luck. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained. Thanks very much, and bye for now.